Good morning. So this is our eighth session, and in the previous lecture we have discussed particularly about the surface tension, and in surface tension actually we have seen that how surface tension acts at the line, or we can say in terms of also have associations in terms of increase in surfaces. Okay. So now we will try to see some other effects of the surface tension. So one very important phenomenon which is called as capillarity. Okay. So basically capillarity is nothing but the association of the surface tension in small diameter tubes. So when we have small diameter tubes, then because of the surface tension, either there takes place the rise of the fluid or fall of the fluid. Okay. So study of these surface tension induced rise and fall of the fluid is something which is known as capillarity. Okay. And typically the smaller diameter tubes in which this phenomenon happens, these particular tubes are called as capillaries or capillary tubes. Okay, so these are called as capillaries or capillary tubes. So typically what happens, say if I have a container, and in this container say I have any fluid filled. For example, this is water over here in the liquid state. Okay, so this is the free surface of the water. Now if I put a tube over here, if I put a small diameter tube inside this, so upon putting the smaller diameter tube inside this, what will be happening? So initially if you see, this was the free surface. Okay, now you will be finding that if water is inside the tube and this is a glass tube, then we will be finding that there will be some rise in height of the water within the tube, and it will form a free surface something like this. Okay, so now it will form another free surface at this location. So this is nothing but a new free surface over here. So this particular curved type of free surface is something which is called as meniscus. Okay, so once we inserted this smaller diameter tube into the water, so within this smaller diameter tube we are finding that there is rise in water. So say water has actually shown some rise through height h. Okay, and after that we will be observing that whenever the free surface of the water will be there inside the tube, this free surface will not be exactly the flat, rather this free surface will be actually curved. So this type of curved free surface is something which is called as meniscus of the this is called as meniscus. Okay, now what basically happens is that whenever I am having a glass surface, and so what I am trying to say is, when I am having a glass tube and water molecules, okay, so adhesive forces between the glass molecules and the water molecules are actually significant in comparison to the cohesive forces between the water molecules. Okay, so in this phenomenon what is happening, adhesive forces are more than cohesive forces. Okay, so if in a system in a combination adhesive forces are stronger than the corresponding cohesive forces, then what will be happening, the water molecules will try to stick to the glass surface. So that is something which is happening over here. So you can see the molecules of water which are very close to the, so particularly in this zone, which are very close to the water, which are very close to the glass surface, these are actually trying to stick to the glass surface, and the molecules which are away, so these are forming kind of a bottom surface. Okay, so This is the reason for formation of the curved surface over here, and this is also the reason for climbing of water in this particular tube. Okay. Now there are different factors which control that how much water will be rising inside the tube. So the important factors are surface tension, diameter of the pipe, as well as the density of the fluid. So these are the three different factors. One is density of the liquid, second is diameter of the pipe or tube, and third factor is surface tension coefficient, which will be deciding how much height will be actually rising inside the tube. Okay. So typically what basically happens, if I just draw the enlarged tube surface over here, then you will be finding that this is the tube surface, and this is the meniscus over here. Okay. So typically if you draw a tangent at this point, if you draw a tangent through the water surface, so this is the direction of the tangent. Okay. So this is a tangent at the solid liquid contact point. Okay. So, and this tangent is actually tangent to the free surface of the water. So this tangent, whenever we measure the angle from solid side, from solid reference within the liquid side, so whatever angle it is making, this particular angle theta is something which is called as contact angle. Is this point clear? So what I have done, I have shown over here the enlarged portion. So this blue colored line is nothing but tube wall. This is wall of the tube, and this red colored line is nothing but meniscus over here. Okay. And at this point, in between the solid liquid contact point, okay, what I have done, I have drawn a tangent to the free surface, and whatever this tangent is making angle with the solid surface whenever measured from the liquid side. So you have to keep this thing in mind. So whenever I am trying to define the contact angle with reference to the solid surface, I can also measure in this direction. Okay, but I am not measuring because this is the air side, this is not the liquid side. When we define the contact angle, we always consider the liquid side. Okay, we have to measure the contact angle within the liquid side. Is this one clear? So now if I extend this tangent, then I can say that in other direction also with the surface of the wall, it will be making this angle as nothing but theta. Is this point clear? So if I extend this angle in other direction, then also it is coming as theta. Please note this point, in your textbook you will be finding that only they will be showing this top portion of the angle. Okay, they will not show this bottom portion. So whenever we measure the angle, it has to be always measured from the liquid side. Okay, and that we are extending to the other side, then it is becoming actually angle theta. Okay, is this one clear? Now, okay, now what we have to do, basically we have to apply some force balance in order to find out that how much can be the capillary rise length. Okay. So to do so, once again I will try to draw the free body diagram. So this is the tube, and this is the container, and in this container first I am having one free surface over here, and then another I am having some curved meniscus, curved free surface, and then I am having another free surface over here. Okay. So now you will be finding that at this point, so this angle we have already seen that with reference to vertical, this angle is actually theta. So at this curve periphery of the interface, we will be finding that in a direction tangential to the interface, we will be having occurrence of the surface tension coefficient sigmas. Okay, so sigmas will be acting tangential direction to the free surface. Fine. Now this tube is nothing but a circular tube. So if this blue colored tube, I try to draw the cross section, so it is nothing but a circular tube. Okay. So the cross section of the circular tube is say circle of diameter d. So now if you see, I will be having over here the surface tension force, and the magnitude of this surface tension force will be nothing but sigma s times pi d, because this surface tension is acting at the interface, and interface perimeter is actually pi d. So pi d times sigma s is nothing but our surface tension force. Okay. Now what will be happening if you see, so this water has some h height over here. Okay. So typically this weight of the water column will also be acting in downward direction. Okay. So I will be having, because whenever I am inserting the tube, I cannot switch off the gravity field. If we are doing this in atmosphere, our atmosphere or earth surface, there will be actually gravity. Okay. So gravity I cannot avoid. So ultimately the weight of this liquid column will be acting in the downward direction. Okay. So if I see that through h height, how much weight of the liquid column is actually suspended in the tube, then I can write weight will be equal to density into volume into gravity. Okay. So density of water, because water is our liquid, and volume will be how much? This is a cylindrical tube through height h. So what is the volume of the cylinder? Pi by 4 d square h. Okay. So this is the volume into g. Okay. Now other force which you can think of is some pressure is acting at this surface, and this pressure is nothing but P naught, outside atmospheric pressure. Okay. And here also we have the free surface, so here also there will be P naught pressure, as any point at this location is parallel to this particular point over here. So in horizontal direction, we will be seeing in the next module that in horizontal direction pressure does not changes. So at different planes in horizontal direction pressure has to be same. So that's why at this point from bottom direction also I will be having nothing but P naught pressure acting on this. Okay. So pressure is cancelling out from both the directions. So ultimately I will be finding that for this type of situation, after accounting for all the forces, now fluid is in static condition, so that's why there will not be any shear stress over here. Okay. So after accounting all the forces, if I do a force balance in vertical direction, then this FST, what I have written over here, sigma s into pi d, this is acting at an angle theta with vertical. So in vertical direction it will be forming sigma s into pi d cos theta as the force. Okay. And this must be equal to weight which is acting in downward direction. Okay. So this will be equal to rho pi by 4 d square h into g. So here pi will cancel, 1d will cancel out, and from here we will be finding that h is nothing but equal to 4 sigma s cos theta divided by rho d g. So this particular equation is very important. This equation is actually called as equation of capillary rise. So as I told you earlier also that we have some factors over here. So one factor is density, other factor is diameter of the pipe, coefficient of surface tension, and one important factor which initially we could not anticipate was actually contact angle. Okay, so contact angle, cos of contact angle is actually also coming into picture. Okay, so this contact angle is having very important implication now. So for any surface, if contact angle is greater than 90 degree, then what will be happening? Then the nature, the direction of the surface tension force will be changing. Okay, it will be opposite. So if the direction of the surface tension force is changing, then it means we will be having formation of capillary fall. Okay, so in place of capillary rise, we will be having capillary fall. Another important point is that, so this height is nothing but inversely proportional to diameter. So it means smaller is the diameter for a given liquid, more will be the height of capillary rise. Okay. And if you go to larger diameters, then capillary rise height will be very small and almost negligible. Okay. Then third important observation is that if you have a liquid of lesser density, then also if you have identical situation, that same diameter tube, but and same coefficient of surface tension, but one liquid is of say smaller density, one is of larger density, then also the smaller density fluid will show more height of capillary. Okay. So typically this example which I have considered over here, particularly considering the angle, I told you that this is nothing but say situation with the water. Okay. If I consider the another liquid which is also very commonly used in majority of the fluid mechanics devices, particularly for measurement of pressure, that is nothing but mercury. Because mercury is a very heavy liquid metal and it is at atmospheric conditions it is easily available in the liquid form. So that is the reason it is also popularly used in many pressure measurement devices, which we will study in the next module. Okay. So typically, if I see that I have a pool of mercury, and inside this pool of mercury, if I dip a capillary tube, then what I will be finding? I will be finding that the contact angle. So in case of mercury, the cohesive forces between the molecules are stronger in comparison to the adhesive forces with the glass surface. Okay. So that is the reason whenever mercury will be staying, it will form a meniscus something like this. So this will be the meniscus of the mercury, okay, in a glass tube. Okay. So because of this, if you draw a tangent at this point, so you will be finding that when you measure the angle from the liquid side, so this is your contact angle theta, and this theta over here is nothing but greater than 90 degrees. So if theta is greater than 90 degrees, cos theta in the previous discussion will become negative, and we will be finding that the surface tension force will be acting in downward direction. So that is the reason whenever I have shown the mercury, so you can see the normal free surface of the container is actually at higher level, and this free surface is within the tube is at lower position. So this is the H. This is nothing but capillary fall. Okay. Is this one clear? Now this contact angle is a very important parameter, and it will find its applications in many areas. So one simple example is, say if you have a solid surface, second solid surface, third solid surface. Okay. In one of the solid surface, if you place a water droplet and if it is forming shape something like this. In other surface, say water drop is forming shape something like this. And in third surface, it is forming shape something like this. So now you can define the contact angle in three different situations. So here if you draw a tangent, this is the contact angle theta. Here if you draw a tangent, then this is the contact angle theta. And here if you draw, then this is the contact angle theta. Okay. So typically for a water drop, if you have a water drop and it is resting on a solid surface, if this contact angle is less than 90 degrees, then we call the surface as hydrophilic. And if this theta is nearly in the range of 90, so it means it is greater than 90 degrees, then we call the surface as hydrophobic. So if you see the same volume of the drop in all three cases, in first case it is trying to wet the more portion of the solid. Okay, so it is trying to wet the solid. In second situation, it is trying to do a situation where actually the contact surface of the liquid with the solid is less, and in third situation it is very less. So when this contact angle is greater than 150 degrees, then the surface is called as super hydrophobic. then typically the surface is called as a super hydrophobic surface. Okay, and if you see, if you go through your advanced knowledge, then you will be finding that typically for designing different boiling surfaces, condensation heat transfer surfaces, or even removing the heat from microelectronic devices, actually this type of surfaces are having plenty of applications. So there we do surface treatment in order to take some advantage of particular kind to achieve the enhanced heat transfer rates, particularly for heat transfer applications. Okay. So now whenever we talk about the solid surface, so we can have two different situations. One situation is if I place any volume of the liquid, that particular volume of the liquid can completely spread in the form of a very thin film. Okay, and in other situation it can rest something like this, as I have shown in the previous cases. Okay, so the situation where it completely spreads over the surface in the form of a thin liquid film, this is called as complete wetting situation. So typically if you drop a water volume over a glass surface, you will be finding almost a complete wetting situation, and theta will be approaching almost to 0 degrees. Okay, and when you are having this type of situation, when theta is say greater than 5 degrees, it is not very small, then particularly we call as nothing but the situation of partial wetting. Okay, and the scenarios like where we can have complete wetting or where we can have partial wetting, this is something which is defined by one important parameter which is called as spreading parameter S. So we have one spreading parameter S which can define that whether we will be having complete wetting or we will be having the partial wetting. Okay, so S is nothing but defined as the surface energy per unit area for a dry substrate. Okay, so say if you consider that you have a substrate of area A, surface area A, and it is dry, means in its surrounding there is air only and this is a solid. So how much will be the surface energy for a dry substrate? So surface energy for a dry substrate will be sigma SA. So SA means surface tension or interfacial tension in between the solid and the air. So that will be for a dry surface. Okay. Now if I do minus of surface energy for a wet surface. So for a wet surface, what I will be doing, say I have contained some liquid over this surface now. Okay, so now if you see, in case of a wet surface, one surface energy will come because of the surface interaction between solid and liquid. So between solid and liquid, now there is a contact between the solid molecules and the liquid molecules. So one surface energy is because of sigma solid liquid, and you will be finding that just at this interface you will be having the contact in between the liquid and the gas as well. Okay, so you will be having some surface energy because of liquid and air interface. Is this point clear? So this is nothing but spreading parameter is nothing but this is the surface energy for dry surface, and this is the surface energy for wet surface. Okay, so if S is greater than 0, and in one situation S can be less than 0. So in one situation we will be having partial wetting, and in one situation we will be having complete wetting. Okay, so where do you expect that we will be having complete wetting? S will be less than. Okay, So in what situation we will be having complete wetting? When S is greater than 0 or smaller than 0? When S is greater than 0, in that situation we will be finding that we will be having complete wetting. Okay, and when S is less than 0, then we will be having partial wetting. Is this point clear? So basically what happens, if you have a drop, if you have a solid surface, and over this solid surface if you have a drop, okay, so this drop, once it has settled, okay, it will be forming one angle. So this is your sigma liquid air. Here there will be one sigma solid liquid, and here there will be one sigma solid and air. Is this one clear? This is a solid surface where we are having contact in between solid and liquid. There we will be having interfacial tension between solid and liquid. Where we have solid and surrounding air, there we will be having surface tension between solid and air, and where we are having liquid air interface, there we will be having surface tension in between liquid and air. Okay, so we know that this angle, whatever the surface will be making from liquid side, that is nothing but a angle theta, contact angle. Okay, so if you try to do a force balance in horizontal direction, you will be finding that sigma SL plus sigma LA cos theta is nothing but equal to sigma SA. Okay, and from here if you try to identify the angle cos theta, that will be becoming equal to sigma SA minus sigma SL divided by sigma LA. So this is one very important equation which can give us the final equilibrium shape of the droplet, which we will be finding over a surface. Okay, so this particular equation is called as Young-Laplace equation. Okay, so this particular equation is called as Young-Laplace equation. Now in this equation, if you consider cos theta equal to 0, okay, so if you consider cos theta equal to 0, then what you will be finding, that you are having the situation of complete wetting. Okay, and if you consider that you have some angle, then actually you will be having the partial wetting. Is this point clear? This famous equation, this is very famous equation to determine the equilibrium shape of a droplet, and this particular equation is called as nothing but the Young-Laplace equation. Okay, now this is all about the surface tension and its associated phenomenon of capillarity, whatever is required from the understanding point of view for your course fluid mechanics. Now today we will try to practice some of the numerical problems based on viscosity and surface tension. Okay, so let's talk about problem number 1. So let us consider that we have an inclined solid surface and its angle of inclination theta is nothing but 15 degrees. Okay, and over this solid surface we have a thin film of liquid. So this thin film of liquid, say, has height h, which is nothing but equal to 1 mm. So this is 1 mm height. Okay, now I have a solid surface of mass m which is on this liquid film and it is moving in downward direction with velocity v. And v velocity over here is nothing but the terminal velocity of this solid. So v is terminal velocity of the solid block. Okay, and we have other given condition that mass of the solid block is 6 kg and area which this solid block is wetting or contacting with the liquid, that is nothing but 35 centimeter square. Okay, and it is given in the question that we have SAE 30 oil which is forming this liquid film and this oil is present at 20 degrees Celsius. Okay, so now what we have to do, we have to refer to the property table and from the property table we have to determine nothing but the viscosity of this oil. Okay, so viscosity of this oil at the given conditions is, if I refer to property table, it is nothing but 0.29 kilogram per meter. So this is our viscosity of the oil. Okay, now it is asked in the question that you have to determine this velocity v. So you have to determine velocity v. First you have to tell me what do you mean by terminal velocity of our object, because then only we can determine it. Velocity which is, yes, so any velocity which is acquired by the substance without its acceleration. Okay, if there is no acceleration, then it will be achieving some uniform velocity. So that particular velocity is called as nothing but the terminal velocity. Okay, so for example, whenever you will be placing this object on this liquid film, so initially this object will be stationary and then from the stationary it will start accelerating and it will try to acquire a certain amount of velocity. Okay, so the period from its zero velocity to that uniform velocity, in that period it will be having certain acceleration also. Okay, but now we are talking about the period of terminal velocity. It means the condition when there is no acceleration within the object. Okay, so now can you tell me how we can solve this? We can balance out mg and viscosity. Okay, okay, so that is correct. So how to find out the viscous force? First you tell me what will be the direction of viscous force in this. Parallel to the surface. So this point is correct. So say parallel to surface, this will be my F viscous force. Okay, how to find out this viscous force? 6g sin theta. Okay, 6g sin theta you are talking about. Okay, so you have done the force balance also. I want to find out the value of viscous force in terms of velocity. How to find out? One by okay, so for finding the viscous force, we know that we have one very important relation, that viscous shear stress is nothing but mu times du by dy. Okay, so now within this liquid film we have to see how our du by dy is actually varying. So that we have to first calculate. Okay, so if I draw the enlarged view of the liquid film, then this is my solid surface and say this is the film over here and here I am having the solid surface. So you will be finding that if I take any cross section within the film, then at this point, because solid is stationary, so at this point velocity of the liquid will be 0. Okay, but at this point whatever the liquid layer, this solid is moving down with velocity v. So whatever the liquid layer will be at this point, that will also be having velocity v. Okay. So now I have to take some assumption for the velocity profile. So let us consider that within this liquid film we have nothing but linear velocity variation. So if I assume the linear velocity profile, then what I can do, at this point velocity is 0 and at this point velocity is v. So I can draw a straight line and this will be my velocity profile within the liquid. Is this point clear? Now this height is h. So if you have to calculate du by dy, then how much it will be? So for this straight line, if you calculate now du by dy, that will be becoming nothing but equal to v by h, considering the linear velocity. Fine. So from here my tau has become mu times v by h. Fine. Now what will be viscous force? Viscous force is, so the definition of shear stress is nothing but tangential force per unit area. Okay. And viscous force is a resistive force. So if an object is moving in downward direction, so viscous force at this surface will be moving in the will be acting in the upward direction. Okay. So I will be having F viscous as nothing but tau times of contact area. So from here F viscous becomes equal to mu v by h into area. Now you have area also given, mu also given and h is also given. V you have to find out. So in terms of v, can you tell me if you substitute all the values what I will be getting? Tell me the mathematical number. 15 point. Okay, 15.3 times v. So this much Newton of viscous force is actually acting here. Okay. Now this force is the resistive force, but there will be some driving force also which is balancing this. So in this situation, if you see, this is your mass m, it will be having weight acting in downward direction as mg. Okay. And what will be this angle? This angle will be theta. So the component of this force parallel to the viscous force is nothing but mg sin theta. Okay. So the component of this force parallel to the viscous force is mg sin theta. So I can say that F viscous from the force balance is equal to mg sin theta. Now the importance of this terminal velocity has come, because we are determining the terminal velocity, that's why we have not taken the inertial force over here, mass into acceleration of the object. Okay, so if we are not talking about the terminal velocity, then mass into acceleration also has to come. Okay, so over here acceleration is 0 because it has already achieved its velocity. So now if you do so, you will be finding that F viscous is 15.3 into V and M is 6 into 9.81 into sine of 15 degree. Can you tell me how much is the final velocity? What is the final value of the velocity? Is it 15 meter per second? Okay, so velocity of the block will be 15 meters. Fine. Then we have problem number 2. So yesterday I have given you problem. How many of you have calculated? Anyone has done that problem? 2 different bubbles are coalescing and forming a single bubble. Have you done it? No one has done. Okay, let me repeat it over here. So I have a bubble of diameter d1, another air bubble of diameter d2, and they are forming third bigger bubble. Once these are coalescing, these are forming a third bigger bubble of diameter d3. So everywhere outside pressure is P0. This bubble is of say air, and this phenomenon is happening at isothermal conditions. And consider that there is no mass loss. It means if m1 is the mass of the first bubble, m2 is mass of second, that is nothing but equal to m2. And this air can be considered as an ideal gas. So ideal gas means PV equal to mRT I can apply over here, or simple PV equal to RT is also, if I write it as capital, if I write capital V then mRT. So PV equal to mRT. This I can apply. Okay. So now can you tell me what will be the conditions? How I can determine this? PV by V equal to, so this M1 plus M2 equal to M3, I can write P1 V1 plus, can I write P2 V2? Because it has to be by RT which is equal to, now RT will be cancelling out everywhere. So ultimately I will be getting that P1 V1 plus P2 V2 equal to P3 V3. Okay. Now can you tell me what will be P1 in terms of diameter? P1 will be equal to P0 plus 4 sigma by D1. Okay. This is a, here also air and outside also air. So because of that we have to consider 2 times. Okay. So for soap bubble this was only the relation. Then P1 we have written, what will be P2? Similarly we can have P3 equal to, okay, and then we can also substitute V1, V2 and V3. All are sphere. What is the volume of the sphere? It will be 8 for soap bubble. Okay, so this situation is identical to a soap bubble. Why? Because I am not saying that outside I have liquid. Outside also I am having air. So one interface is from this side and one interface is from this side. So that is the reason that in place of 4 then we have to consider over here 8 sigmas. Is this one clear? Please check your relation from the previous lecture. If for a soap bubble it is 8, then it should be 8 over here. Okay. Now volume of the sphere. What is the volume of the sphere? 4 by 3 pi r cube. Okay, in terms of diameter it will be becoming how much? Pi by 6 d cube. Okay, so pi by 6 d1 cube. So let us substitute in this equation. So what I will be getting ultimately? P0 plus 8 sigma s by d1 into pi by 6 d1 cube plus P0 plus 8 sigma s by d2 equal to P0 plus 8 sigma s by, so if you see here, P naught is known to us, sigma s is known to us, d1 d2 are known to us. So from this equation I can calculate nothing but diameter d3. Okay, if I substitute different values, then I can calculate diameter d3. Once I have the value of d3, I can calculate what is the pressure within the final bubble. Okay, is this one clear? Now let me give you some more problems. So let us consider that we have two plates, horizontal plates, and between these two horizontal plates we have some water filled. Okay, and from the center this water is, say, having some distance r, and spacing between the plates is h, and contact angle over here is theta. You have to determine how much will be the attractive force between these two plates. Okay, so that is something which you have to determine. Fine. Second problem is, you have a big container of water, and inside this container of water you have two horizontally, so you have two large plates. So these are two plates which are having W spacing between each other, and say B is the width of the plates. Okay, and whatever the meniscus is being formed over here, say that meniscus is having contact angle theta. You have to determine this capillary rise. Fine. So these are the two problems which you can try by your own. Sorry? First one? Values? Okay, calculate it. Okay, try these two problems. So similar kind of problems, actually you can go through your textbooks. You can solve first the solved examples, and then you can solve the unsolved problems are also given. And once this next module is also over, after that I will be giving you one assignment which will be comprising of questions from both module 1 and module 2. Okay.